Yes, hello. Good day, ladies and gentlemen. So good to be back with you again in this channel where we talk about engineering, we talk about architecture, and we talk about construction. Today I thought of making a video so that we discuss a very interesting topic, and it's something which I think most people do ask, and I really want to discuss it here today. So the topic of today is finite element methods. Really, what exactly is finite element methods? That is something which everybody must be asking, and I want to break it down in this video very well so that it never intimidates you again. So if you want to understand finite element methods, just keep it here and watch till the end so that it will never intimidate you. Well, so what exactly is this idea of finite element methods? Let me just write it down. Let me just write it down so that we have finite element methods. What exactly is this finite element methods? Well, just to begin with, it's good to note that every material, resists forces or resists stresses by the strength of their bonds. What I mean is simply this. As usual, let us do sketches so that we could understand exactly what is going on. If you have a material, say you have some simple piece of rod like this, and you apply some tensile load on this rod, this rod will resist this load by the strength of the bonds between the particles of this material. So if we have a particle here, we have a particle here, we have a particle here, then the strength of these bonds, we have bonds which are attaching these materials together, so the strength of these bonds is the one which resists these tensile loads. That means for you to exactly know the maximum stresses which this material is going to carry, let me just use a different color for these bonds. These are the bonds, these are the bonds between the particles, and so for you to know the maximum stress which your material can carry, that means truly you have to analyze the bond strength. You have to analyze the stresses between these particles, and you have to analyze all of them, so that you come to a conclusion that all of them, the stresses between all of them, and that it is not exceeded, so that your material is safe. Well, look at this. You have a beam. How many particles does it have there? Millions of them, and you need to really check whether it is safe. So that means you have to know the stresses between all these particles, these million plus particles, to ensure that your material, your design is safe. That is impractical, and really it is the right thing to do, but it is impractical, it is laborious and of no use. So what happens? Why finite element methods came in? Finite element methods simply wants to break this scenario down, into solvable parts. So the term finite, where from? We have next to infinite number of particles here, which will take you your entire lifetime to solve, to know the stresses between the bonds, so that you check with the applied load whether it is safe. But then we want to simulate this scenario here. We want to simulate it by breaking down this material into given number of particles, So we want to break down this material. Let me just use a different color for this. We want to break down, which color do I use? Okay, we want to break down this material. Let me just use red. So this is the material, We now want to break it into known number of elements, We want to break it into known number of elements so that these elements, let me just do that. Let me say I want to break it into, maybe, let's say, this is my original material, but now I want to, I've broken it into this number of particles, So these particles here, these nodes, these elements here, these nodes here represent our particles here. Do you get it now? We are breaking this problem into unsolvable thing, millions of particles into solvable number of particles, so that we have one of our particle there. So we consider these our nodes, we consider these our nodes as our particles, and so that the stresses in this is good. There is a different color for that. So the stresses in this, the stresses between these particles, the stresses between these nodes will be the stresses in our material, right? Yeah. So that we analyze this using finite element softwares, and we get the maximum stresses in these materials here. Then we can tell where our material will break. Well, this is just a method of approximation, estimation. Because really, we have this thing. Let me use a different color. We are breaking it down from this unsolvable problem, to this solvable problem. This is where finite element comes in. This is the basic principle of finite element analysis. So I think it will not intimidate you again. Let me just repeat this very important point, that for a designer, for an engineer to make a conclusion that their designs are safe, the engineer should analyze the stresses between these particles in this material, stresses between every particle, so that they can make a conclusion that the design is safe. That is not possible because we have infinite number of particles. We have millions of them, really. So we need a way of breaking this down into known number of particles, which is what we have here. We break it into known number of particles so that these nodes represents our particles. Then the bond strength here will represent the strength of material. I hope the idea is now home. This is the basic principle of finite element analysis. Well, this process of breaking it down from unsolvable to a scenario to a solvable scenario, it is called discretization. Yeah, we want to just break it down into elements. It is called discretization, so that you can solve that problem. So how exactly do you solve that problem? Because well, there are computational methods, there are mathematical formulas which can be used to find the stresses. That is a story for another day. Today I just wanted to bring in the idea, and the basic principle behind finite element analysis. Well, this reminds me of a very interesting quote by Dr. Dykes. I think, let me just look for that, and I make it visible in my screen so that we can really read it together. Let us see what Dr. Dykes had to say about engineering at large. Okay, let me look for that. Let me just look for that. Good. This is what Dr. Dykes, Dr. Dykes had practiced as a structural engineer. He was a member of the British Institution of Structural Engineers. In 1976, after interacting with materials and doing a lot of designs, this is the conclusion which Dr. Dykes made. What did Dr. Dykes say? That engineering is the art of modeling materials we do not wholly understand into shapes we cannot precisely analyze so as to withstand forces we cannot properly assess in such a way that the public has no reason to suspect the extent of our ignorance. As you advance in this career and as you advance in the design, you really come to understand that Dr. Dykes was really correct. Was really correct. What is Dr. Dykes saying? It is the art of modeling materials we do not fully understand. Look, this material here, we do not fully understand it. That is the idea of the matter. We do not fully understand it. We do not fully understand how this material is behaving, but we can just simulate. We can just come up with rough ways of analyzing that material, and from previous studies we can know the strength of that material. Then we can use that to do our designs. So again, we don't know it all. It is just dealing with materials we do not fully understand. So the public has no reason to suspect the extent of our ignorance. This is the basic idea of finite element methods. Well, maybe to show you how this is done in the computer environment, let me just look for something to indicate to you that. Well, I'd like to show you this. This is what I was saying. We have a complex material. We have a complex material here. We have a complex material, this one here. But we want to analyze it so that we can know the stresses, the maximum stresses in this material, the maximum deflections in this material, right? What we do is we break it down into elements. These are the elements. After breaking it down into elements, the elements are looking like these ones here. If you can see what is here, these are the elements with nodes, with nodes and with bonds here. So for you to know the strength of this material here, you need to know the strength of this bond. That is the basic idea. So we break it down, into elements so that the maximum stress, let's say the maximum stress was somewhere here. The maximum stresses are somewhere there. That means we have to analyze this element here and get the stresses between these bonds, the stresses between these particles, here, so that we shall have approximated the strength of this material. But remember, if the strength was here, let me say, I can use a dark color. So let me say we find the strength in this bond, the strength in this bond, the strength in this bond. Well, maybe the strength between this one here, between in this triangle here, is even more higher than the stresses in these ones, right? Yes, but what we do is just we come up with the not approximate, which is nearly there, which is nearly there. So what happens is that the finer or the smaller the elements, the more accurate the results, So as a designer, if you're breaking your material, you have to break it down into smaller number of particles. But the problem with that is that the smaller the number of particles, the longer the time required for these computations to be done, right? So as a designer, you can just decide, to break it into reasonable number of particles so that you can get your results a bit faster, because design really means want to take care of time, want to take care of safety, you want to take care of the economy bit of it, want to make it very cheap, so that you save time, and also you make it safe. That is why we also have the factor sort of safety, which you apply for materials and also for loads. That is according to limit state design principles. So this is the idea behind finite element methods, that for us to know the strength of this material, we need to know the strength of the bonds, and if we find the maximum stress in those bonds, then we know the maximum load that material can carry. But because we cannot really tell the maximum stress, because we'll have to analyze every bond, which is not possible, we break it down, we simulate that, we break it down to simpler number of elements so that we get stresses in those bonds. Well, this one here is just to indicate that we need mathematical, these stresses here, they are mathematical equations which can be used to determine them, right? The mathematical bit of it is a story for another day. Today I just wanted to bring the basic principle behind finite element analysis, because I do understand that once you miss the principle, then it becomes very hard for you to understand even the mathematics bit of it, because you'll be doing something you do not really understand, so those stresses can be determined through some mathematical equations, the differential equations. Well, maybe just to show you another thing, it's so interesting. Finite element analysis can be used in several number of fields. Let me just look for a picture maybe to show you that. Oh, there. If you look at this one here, this photo here, this is a picture of a slab analysis. What we do is we apply loads on a slab, then we do finite element analysis so that we see where our slab is going to break. We see where our slab is going to break. So maybe let's say that our maximum stress is here. Let me pick color red. Yeah. So probably from this analysis, I don't know the color codes the designer here used, but seemingly maximum stresses are at these corners. So once you know the maximum stresses, you can really design your material to carry those stresses, so that it doesn't fail. So you see what is happening here. The designer here has just broken this material into finite number of elements, so that they can analyze this element. They can analyze this material to see the maximum stresses. So as you can see, we have, I think, according to him, I do not know the color code they used, but this red must be the point of high stresses. These colors will tell you, where your maximum stress is, so that you know what to design for at what point. So that is for that slab. You can see the picture here again. You can see a bigger picture here. We have this is a building. The loads have been applied, then finite element analysis, stress analysis is done, so that the stresses in these our slabs are known, so that we can design that slab to take the stresses, and also the stresses in these our I think this is a lift core. We also know the stresses, so that we can design for that. It is also used in aeronautical engineering. You can analyze the stresses in your aeroplane wings, so that the materials you should be using for that, and the shape you should be using for that. Very interesting. Finite element analysis is just interesting. Just very interesting. Just very interesting. This one is a beam. A load is applied here, as you can see, and this beam has been broken into finer number of elements. Finer number of elements, so that we determine the stresses. And from this look, the maximum stress is at this point. So that is what we design our material to carry. The maximum stresses at that point. Well, what again should I say about this? Maybe just a final bit of it. Back in history, in those old days, yes, back in the history, in those old days, the car manufacturers didn't have a way of telling the level of damage which their car will be subjected to, when the car was involved in an accident, right? So what they used to do is that it's so interesting. What they used to do is that they manufacture several designs, say 10, and they want to see which design is safe to be taken to the market, which design is safe to go to the market. So what they would do is that they make 10 designs, right? After making 10 designs, they run these vehicles into a wall. So we have a wall of known strength, Then the first vehicle, they will run it into the wall. They see the level of damage. The second vehicle, they will also run it into the wall. They see the level of damage. They run them all at the same speed, from the same distance. Then the walls are of the same strength, so that they will see the level of damage in every vehicle, in every car, So the car which will not have a lot of damage will be released to the market to be the safe car, So look at that scenario. They make 10. Maybe only 2 designs passes. Only 2 designs are safe. That means they've wasted a lot of materials in other 8 designs, They've wasted a lot of time. They have wasted a lot of manpower, in 8 designs, because only 2 designs are safe to be released to the market. So what happens is that with finite element analysis, we have softwares which can analyze this scenario, which can analyze this scenario. We have softwares which, if you tell them what the wall is made of, if you tell that software what the wall is made of, tell the software what this car is made of, and tell the software the speed of this car, this software will be able to tell you the maximum stresses which will be in this car, so you will know the level of damage in this car. This is an example. So even before you manufacture any car, you already will be knowing which car is going to fail and which design is going to pass, right? So that you don't waste materials and time. Very interesting. This is the power of finite element analysis. This is the power of finite element methods. Let me stop here for now. I think I just have to stop here because it is interesting. If we start to speak about it, then we might speak about it forever. Here you can see we have this car here. It is just broken down into elements, which you can now analyze and see the stresses between the stresses in the bonds, and compare with the strength of that material, and you will tell the level of damage. Very interesting, very interesting. Let me just stop here. If you have any questions, please don't forget to put them in the comment section. If this video is good to you or has added some value to you, please like it and share it with your friends, so that we will continue making engineering enjoyable together. This is the end of it. If there is no questions, maybe let me do the final summary. Let me do the final summary of what we talked about. Then we call it let me do the final summary. Well, let me do the final summary. Number one, we said that for you to know whether your material is safe, whether your design is safe, you have to know the strength of every bond in your material. So if that is a particle and this is a particle of a material, then you have to know the strength of this bond, which is impractical, yeah. So what happens is that finite element analysis breaks that material into given number of elements which represent this scenario, which represent this scenario here. So after breaking it into a given number of elements, the finite element analysis softwares will run the analysis and will tell you the stresses at different points in your material, the stresses, different points. Number two, which I think is worth noting, is that these stresses are determined through mathematical equations, the differential equations. Those differential equations, the differential equations, you can as well use them to calculate the stresses manually, but that will take forever. That is where the idea of finite element analysis comes in. Well, what other things worth remembering from this class? What again is worth remembering? Let me just check through. Well, another thing which is worth remembering is that we cannot really be accurate in this. That is why finite element analysis is here, just to do the simulation, to do the discretization, so that we can determine the stresses. I think I'll have to stop here. I really appreciate you. Continue supporting this channel. We want to make it a very, very superior channel. Where engineers will be really engineers, So share with me your ideas of finite element analysis. Share with me your experiences with finite element analysis, whether in your designs or in your campus, where you used to study it. Did it intimidate you? If yes, then why? What happened? Were the equations so complex that you could not master? Well, tell me below. I'll be so happy to interact with you and to really also learn something from you. I remember no one knows it all. We're just here to share ideas, right? So if we have a better science, bring it on so that we could understand it. Thank you so much, ladies and gentlemen. I really appreciate you. See you next time. Stay safe. I am Oloji.